So how electrons are organized in an atom is basically important, because based on where the electrons are located, that's going to tell me how big the atom is, how good it is at pulling electrons, if it's willing to share or steal or lose. So we kind of talked about this when we did chapter 5 and determined whether something was ionic or covalent. And again, we'll see that the reactivity of these electrons, or the arrangement of the electrons, are related on the periodic table, and that's how it's organized. So one of the things I want everyone to understand for chapter 9, especially now, this is a hard chapter for me to even teach face-to-face. To do it online, it's even more difficult. And there's no way you're going to be able to see this the first time and understand it. And I always like to kind of talk about how, you know, this is weirder than even the people who developed the concepts believe. So the theories used to explain quantum mechanics were devised by brilliant scientists, Bohr, Planck, Einstein, and a mathematician, Schrödinger, who came up with a mathematical equation to figure out probability maps for these electrons. So if it doesn't make sense right away, it's okay. It doesn't make sense for a lot of people. And I wanted to show that a couple quotes. He's talking about quantum mechanics, what we're going to be learning in the second part of chapter 9. I don't like it, and I'm sorry I ever had anything to do with it. God does not play dice with the universe. Why was this said? Because we'll see that these orbitals that we're talking about are basically probability maps. They're based on probability. We can never fully know exactly where an electron is because they're so small. When we measure them, we change their behavior.
Mm-hmm.
So it all actually started with light. They were working with light, and that's kind of how this understanding of the atom and the electrons and the different orbits or orbitals of these electrons. So we're going to first discuss topics of light, and typically students are more comfortable with light because they've learned it earlier. So light can interact with atoms, and studying the interactions led to understanding how the electrons are organized. Light is not really matter, and this is what's difficult for people to understand. It's a form of electromagnetic radiation, okay? So light is not really matter. It's a way that energy travels through the universe. So electromagnetic radiation, shorthand is EM, and it's the way energy travels through the universe. And we know that the speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. So this is a velocity. So I think I mentioned this in one of our lectures, right? So this speed of light, they use c to show the speed of light. That's the constant. And we don't have to do these calculations. But does anyone know the speed of sound? It's 341 meters per second. So that's basically 3.41 times 10 to the 2 meters per second. So light travels 10 to the 6 times faster. Does anyone know how much faster that is? 10 to the 6? A 1 with 6 zeros?
1 million?
A million times faster. That's why you always see lightning before you hear the thunder, because light travels so much faster. So how do we describe light? There's a couple of characteristics that we want to use. So one is wavelength. Okay, so wavelength. You basically go from crest. Crest is the peak. Crest to crest is considered wavelength. okay? Now you could go from trough, the minima, from trough to trough, and that would also be the wavelength. But typically your wavelength is the distance either between peak to peak or trough to trough. Sometimes they do the intercept and they say period to period. If you've had any type of trigonometry or pre-calc or basic physics, you've been familiar with, graphing waves and things like that. The other thing is I wanted to show you the symbol for wavelength is what's referred to as lambda. And you don't need to know that Greek symbol, but they use that. They write lambda all the time. So I want you to kind of be comfortable with it. And typically your wavelength is, how do we measure, length typically? What's the standard international unit for length?
Meters?
It's meters, it's not inches. Okay. The other property I want you to think about is frequency. Okay. Now frequency, some books, like some physics books, they'll write it as F, like a lowercase f. In chem, we use what's called the nu. It's a lowercase nu. And that nu, that actually, the way it's in this PowerPoint, it looks like a V, like velocity. It's not velocity, okay? That nu, really, I should write on that nu. So we're not going to use the F like they do in physics. We're going to use the nu. The nu is like a V with a little tail on it. It's got like a little curvature to it. God, that's so bad. I'm sorry. So it's got a little curvature to it. If you don't put the tail, it's okay. We're not doing these calculations anyways. I just wanted to show you the concepts of two of these parameters. But basically, the frequency, and it's hard because a lot of people don't really, we're not comfortable with like, revolutions per minute. We don't have the 45s like back in the days with records. So we don't really know hertz, like on the AM, FM radios. People don't use that anymore. We use satellite. But frequency is basically cycles per second. It's a cycle per second, or a hertz. A lot of times the unit for this is just, they'll write it as 1/2, or s to the -1. And what confuses people is, well, what do you mean by cycle per second? So here I have a wave. And I'll pick a different wave here. Let me see. Let's do a different color. Yeah. Here I have another wave. And my drawing is kind of poor, but let's assume that these waves are uniform in their wavelengths, which this is not at all, so I apologize. But so basically, in both of these, there is a wavelength, right? So from trough to trough, that is my wavelength. And it would be the same here. Trough to trough, there is my wavelength, okay? So of these two waves, red light and blue light, which one has the shorter wavelength?
The blue.
Blue.
The blue. And the red would have the longer wavelength, okay? So how does this relate to frequency? Frequency is, if I pick any point in space, so let's say I pick that line as a point in space, and in 1 second, if these are both traveling at the same speed, they're both traveling at the speed of light. So again, c is speed of light. It's 3 × 10⁸ meters per second. And that's in a vacuum. If both of these waves are traveling at the speed of light in 1 second, which of the two would have more peaks pass by?
The blue one.
The blue. So the blue would have more cycles per second. So the blue, and I guess The blue has a higher frequency. So why does the blue have a higher frequency? It has a shorter wavelength. So what does that mean for the red? The red has a longer wavelength, right? So it has a lower frequency. Why does it have a lower frequency? I'm sorry? I didn't quite get that. Somebody, I think, was trying to ask a question, or let me see. Maybe it's in the chat. I'm sorry. I haven't been. Oh, throwback to physics. Okay. Okay. So going back to this, the longer wavelength has a lower frequency. The shorter wavelength has a higher frequency. What do I mean by frequency? The number of peaks that pass this point per second, right? So something that has a shorter wavelength has more peaks passing through this point in 1 second than something with a longer. So really, that's kind of all you need to know. Now, what type of relationship is this? Where if one goes up, the other goes down. We've talked about this before. They're not directly proportional. Directly would be if one goes up, the other goes up. So if one goes up, one goes down. What does that mean? They're inversely proportional. They're inversely proportional. So why are we, why are we looking at waves? Why are we looking at wavelengths and frequency? Well, we're going to talk about light, basically sunlight, right? Sunlight comes in all wavelengths, but it can be basically separated through diffraction, right? So I can take any light source, kind of direct its beam through a slit, and then use a prism, which basically has small grooves, similar in size to the actual light's wavelength, that causes it to bend and diffract. And what do I end up getting? The white light becomes what?
A rainbow.
A rainbow.
Multicolored.
Exactly. We see this all the time. Where do we see this? In places like Hawaii. Why? Hawaii has a lot of rain, a lot of moisture, but it also has a lot of sun. So the small, fine water particles that are in the atmosphere, they're so small, they're at the similar length as the light, that it causes a bending around the water droplet. It acts as a prism. And what do I get? A rainbow. Now, do you need to know the colors of the rainbow? You should, right? That is one thing, but we don't do calculations in here, but you should know the colors of the rainbow. And of course, I have an acronym, a silly little acronym, and you might already know it. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Now, I'm a guy. I don't know the difference between indigo and violet. I really don't. But you're supposed to know it. I'm bad with colors. Indigo, violet, they all look purple, but there is a slight variation. So, light as particles. In the early 20th century, scientists like Einstein saw that light was not a classical wave. And he explained that light acted more like particles, which he called photons. So most people are comfortable with the term of photon of light. It's a packet of light or a packet of energy. when light was shined on metal, we saw that it sometimes ejected electrons. And that's actually what Einstein won a Nobel Prize for. It wasn't for theories of special relativity. We didn't understand it at the time. It was actually for the photoelectric effect, what we're discussing right now, which developed into quantum mechanics. But right now, as we sit, we're sitting under lights and we're being showered by these particles. So when we say radiation, a lot of times people think radiation is bad. Not all radiation is bad. So what I'm trying to show you is electromagnetic radiation, the way energy travels through the universe, there's a whole spectrum. And really the first part of the spectrum is the one that we're really comfortable with, is visible light. And visible light is a very narrow portion of electromagnetic radiation. In fact, it's the most narrow region of all electromagnetic radiation. But if we were to take that narrow region and kind of expand it, what do we get? Roy, whoops, sorry. Let me move this over here right now. Roy G. Biv. We get that spectrum. And if we look for the rest of the electromagnetic radiation spectrum, right, for light, what's right next to the region of red?
Infrared.
Infrared. Now, infrared, we can't see it. It doesn't mean it's not there. In fact, infrared is used for detecting thermal energy. That's why, you can use infrared goggles to see at night because you can see thermal energy, black body radiation, right? So infrared, its wavelength is slightly, its wavelength is longer than visible light. So the infrared's wavelength is too long. It doesn't fit into our eyes, it doesn't go into the back through the pupils to our cornea and retina and actually fit in receptors to stimulate a neurological impulse and let us see a color. It's too big, okay? It's not small enough. And what's a little bit longer than infrared? Microwaves. They're even longer. So these are typically in the centimeter region. And then what else is really long? The longest are radio waves, sometimes called TV waves. That's why if you're ever, how do we get stations? I listen to stations and they're in Tijuana. How do I hear music from Tijuana when I'm all the way up here? Well, the radio waves are measured in meters. So they can travel around, skyscrapers. It's not until you're driving in a valley and you drop down and there's big mountains that what happens to your radio now? I'm really aging myself because I'm sure people don't.
It's staticky. You lose the connection.
You lose it because now the radio waves, even though they're really long, they're blocked by mountains and you can't get it. Right? I'm really, really aging myself here. But anyways, so look at this cell phone right here. Okay, anyways. So I like to show this because it shows that radiation is not necessarily bad. It has many uses, right? So we use, microwaves for radar. We use radio waves for TV and radio. We use infrared for heat lamps, right? And all of these are longer than visible light because red light, okay? And if we look right here, red light, we see 700. Does anyone see the unit that we're looking at? It's nanometers. Does anyone remember what a nanometer is? So 1 meter is 10 to the 9 nanometers. You need 1 billion nanometers, so like nanotechnology, it's really small. you need 1 billion nanometers to equal 1 meter. Red light is 700 nanometers. But like how I drew earlier, what do we notice about blue light? It's smaller.
Smaller.
It's 400 nanometers. That's what I try to depict, earlier when I was drawing those wavelengths and frequency diagrams. So we see that as we move this way, it's getting smaller, right? And you could see it based on the wavelength is the exponent is getting smaller. And as I go to ultraviolet, what do we notice about ultraviolet? Is it going to be smaller or bigger than visible light?
Smaller.
It is smaller. And now, as things get smaller, what do we start noticing? Like ultraviolet, X-ray, gamma ray. What as the light starts getting smaller, what starts happening? Barb, you're doing great. Anybody else? Someone did the chat. Let me look. Blocked, visible, not visible. Well, yes, that's true. Whoever said that, that is true. As it gets smaller, it's not visible anymore. We can't see ultraviolet. So it's too small to fit in our receptors. So yes, but what I'm also trying to say is when you hear ultraviolet, UV, what do you hear? Okay. I wish you guys would use the audio because it's hard for me to look at the sun. Yes, you think of the sun. But is UV good for you? What are they finding out?
It's more harmful.
Yes. Thank you, Andrew. So my generation we were the really neglected generation. Back those days, they never told us. They had sun lotion or protect, but we would go to the beach all day and we wouldn't put lotion. We'd put baby oil and fry ourselves. So what happens? A lot of the Xers have a high cancer rate, right? So why? Ultraviolet. Those electromagnetic radiation particles are so small that they're small enough to penetrate and embed themselves into several layers of your skin, of your epidermis. And they can actually break bonds in the DNA because they're small enough to break bonds and cause mutations. And then what about X-rays? You never think X-rays are bad. When you go to the dentist or you get an X-ray, what do they put on your body to protect you?
A lead apron.
They put a lead apron. Why do they put this dense material? So that the X-ray doesn't do what? Harm your organs, right? Why? X-rays are smaller than, ultraviolet, so they penetrate more than just your epidermis and the few layers. They can actually go through you. In fact, that X-ray, you see this white part? That white part is where the X-ray is getting stopped. So when you it's basically a picture and it has like a film on the back. They shoot the X-ray and whatever is black, so all the black part of the X-ray is the X-ray burning that film. And whatever's white, what do you think happened? The X-ray stopped. Your bone was dense enough to stop it. It went through your skin and your organs, but it stops at your bone. So you're basically seeing a negative. You're basically seeing a negative of film. So a lot of you probably don't remember because everything's digital. They used to have oh God. They used to have negatives. They used to pull through the Kodak little center and I'll shut up, Sean. Okay. What about gamma rays? What do we hear about gamma? Now I know you know this because Marvel comic, the Incredible Hulk, right? He absorbs gamma radiation, right? So gamma's bad. It's really small. It's really energetic. So typically what we're noticing is as light is getting smaller, it becomes more harmful. Why does it become more harmful? It's smaller so it can penetrate more and do more damage. It's referred to as more energetic. But we're not doing those calculations to show the energy values. So I still want you to understand these concepts so when you move on. Okay. So here's kind of another scale. I just show you this. And this gives you another, it does the Roy G. Biv. And again, it shows infrared and then radio. But what I liked about this is it shows, okay, here's a radio wave. It's about the length of Mount Everest. Here, it's about the length of a skyscraper. Now we get into shorter wavelengths, the length of a human, right? 1 meter. 1 meter, humans are we're about 2 meters. A meter is about 3.28 feet. But, 1 meter. And then, smaller, once we get infrared and microwave, we're seeing it's in centimeters, fingernails and pinheads, right? And then when we get to visible light, okay, that's the size of a bacteria. And then ultraviolet, a virus. When we get to X-ray, now we're getting to the size of atom. Gamma ray, nuclear energy, nuclear radiation, now that's the size of the atom. The other reason why I show this scale is they show a prefix that we don't see. It's called an angstrom. And you don't need to know this, but when you go and you look at references and you read things, a lot of times they measure bond lengths and bond angles in angstroms. And an angstrom, you need basically 10 to the 10 angstrom to get 1 meter. So we go from, nanometer, which is, you need 10 to the 9 of those, to pico, which is 10 to the 12. And then femto, 10 to the 50. We always go by multiples of 3. Well, the angstrom is a weird multiple. It's 10 to the 10. And whenever you read research articles, they always show angstrom, so I like to show that. And it's basically an A with a little circle on it. You don't have to worry about this. I'm just giving you another reference to show, relative sizes. Again, this is a very theoretical chapter.